Yes, you're welcome to our lesson number 2 of alkanes. In the previous lesson, all we learned is about introduction of the alkanes. So we understood what alkanes are. We looked at the types of alkanes and then some nomenclature of alkanes. Now, in this lesson here, I want us to look at isomerism in alkanes. From our previous lessons, the word isomerism is not new to us, but specifically now in alkanes, which form of isomerism do we have there? Now, isomerism have 3 types of structure isomerism. These ones have only structure isomerism. Remember that isomerism has what we call structure isomerism and stereo isomerism. But alkanes have only structure isomerism and exhibit the 3 forms of structure isomerism. So I'm going to say that alkanes with it can be not specific like that. Alkanes form all the 3 types of structure isomerism. All the 3 types of structure isomerism. And that is i.e. there's what we call chain isomerism, but there is also what we call position isomerism, and there is also what we call functional group isomerism. Functional group isomerism. One thing that we also need to know is that these types of isomerism in alkanes are only exhibited by alkanes with more than 3 carbon atoms. So you don't find ethane having isomers. You do not find propane having isomers. So we can say that something to note, that isomerism in alkanes, begins from carbon atom number 4, from carbon atom number 4, and this means that ethane. Therefore, ethane, this structure formula, and propane, this way structure formula, CH3C triple bond, CH, those ones do not have any form of isomerism in them. But when we go to 4 carbon atoms, then isomers start to come in. And we are going to look at some examples here of some isomers. And let's begin with chain isomerism. Chain isomerism. In the definition, we say that chain isomerism results in the different arrangement of carbon atoms within the carbon chain, resulting into what we call branched and straight chain isomers. That's what we said in the definition. So we can just refer to it and then say that if we are given, for example, molecular formula C5H, remember when we are writing the molecular formula, we follow the general formula, which we said is CnH2n minus 2. So if this is 5, what will be our H? You say 5 times 2, that's 10, subtract 2, and this will be 8. So when we are generating our first isomer, we first write the straight chain. And if you're not very good at this bonding thing, you can first get a pencil somewhere and then try sketch 5 of them. And then if there are 5, since this is an alkane, there must be a triple bond somewhere. So I'm going to place the triple bond at the last 2 carbon atoms there. And so if I place the triple bond there, I will get my first isomer as CH3, CH2, CH2. They are supposed to be 5, so we have CH2 and C triple bond. This is 1, 2, 3, 4. So we are supposed to put in between the last 2. So we have CH. Remember, this skeleton here would help you to know the number of hydrogen atoms on each of the carbon atoms. Like here we have 3 such that the bonds are 4. Here we have 2 such that the bonds are 4. Here we have 2, bonds are 4, like that. And then here they are already 4, so we don't put. That's why we come up with this. Now this is our first chain isomer. And then what we do, if we are looking at chain isomers, the difference is in the arrangement of the carbon atoms. So if these are 5 carbon atoms arranged in the straight chain, what we are going to do is simply to create a branch. And branching does not take place on the first carbon atom. Branching should take place in the middle there. So what I'm going to do is to write now 4 carbon atoms in a straight chain and create a branch somewhere. Like what we had here, instead of 5, I am going to write 4. And I will put a triple bond in the last 2, so that I don't change the position of the triple bond. And then I put a bond. Now, I put a branch. Branching cannot occur here, but branching can occur in the middle. It cannot as well occur here because already there is full bonding. And it cannot occur on the first one because branching cannot occur on the first and on the last. It occurs in the middle. So the only carbon atom left for branching to take place is actually now this one here. So we shall put our carbon atom there. And if every carbon atom must have 4 bonds, then what do we have? Let's write. This is CH3, C. This is already having 3, so there is now 1 H there. And then the branch is C, and it has to have more 3 hydrogen atoms to make 4 bonds, CH3. And then we go to C triple bond, CH, like that. Now this is another isomer, reflecting the same molecular formula. 5 carbon atoms and 8 hydrogen atoms. Now these 2 compounds are isomers to each other. What's the difference in them? The difference is in the arrangement of the carbon atoms. So this is a chain isomer to this. If we are naming them, we shall name and say this is supposed to be pentyne, but because they are position isomers, as we said, this one should now be positioned. This one we should locate the position of the functional group. So this is pent. Then we say what's the position? Lowest number possible. Carbon atom number 1. This is pentyne. When we got here, the main carbon chain has 1, 2, 3, 4. So it's a butane. But this time, there is a methyl group on which carbon atom we number, giving this one number 1. So number 1, 2, 3. So we shall say this is but. Actually, now we have to locate even the position of the methyl group. So methyl group is on the 3rd. So we say 3 methyl, and then 1, 2, 3, 4. So this is but. 3 methyl, but, 1 N. 3 methyl, but, 1 N. Like that. So this is what we call chain isomerism. It occurs when the carbon chain or the carbon skeleton differs due to branching off. Now let's look at chain isomerism. Let's look at chain isomerism. Now chain isomerism, let's look at position isomerism, sorry. Now position isomerism. We said that in this form of isomerism, the carbon chain is the same, but the difference is in the position of the functional group. And this time our functional group is the triple bond. So we are going to say that if we have molecular formula, for example, C4H6, okay, we can write the first isomer. The first isomer is normally the straight chain. And that means if I had 4 carbon atoms, I would put a triple bond somewhere at the end. And then I would put the hydrogen atoms. So here we shall have 3 hydrogen atoms. Here we shall have 2. We cannot have any there because the carbon atoms already have 4 bonds. And then at the last one, we shall put 1 hydrogen atom. So we can now write that and say, this is CH3, CH2, C triple bond, and then CH. So that is the first isomer. Now if we want to create a position isomer, what we do is now to move the triple bond to the next pair of carbon atoms within the chain. So such that instead of being at the end, we can put in the middle there. And so the resulting isomer would be CH3C triple bond C, CH3. These two compounds share the same molecular formula, but have different, positions in which the carbon atoms are. So this is but1-ene. This one here, but1-ene. But this is but2-ene. And so, but1-ene and but2-ene are position isomers to each other. And then we have the other case now. We have the other case of functional group isomerism. Functional group isomerism. Now, functional group isomerism arises when compounds share the same molecular formula, but the compounds have totally different functional groups. Meaning that every time we have an alkyne, there is another compound with a functional group which is not a triple bond. So we want to find out which one is that. So we are going to say that alkynes are isomers to compounds called dienes. To compounds called dienes. A diene, just as the word is, diene, it is a compound with 2 double bonds. These dienes, I can write that one here, that dienes are alkenes with 2 double bonds within the carbon chain. Within the carbon chain. For example, this one can even start with as low as propane. For example, C3H4. C3H4. When we write this compound here, we are going to write propane, CH3C triple bond, CH. This is propane. Now, the moment I write propane, there is another compound which does not contain a triple bond, but rather 2 double bonds, but also has the same molecular formula. And so that compound is a functional group isomer to this alkane called ethane. So what are we going to do? If we have our arrangement of carbon atoms there, 3 of them as the molecular formula is saying, then we are going to put 2 double bonds. So 1 double bond here, another double bond is there. And so we write the structure now, putting the hydrogen atoms, ensuring that each carbon atom has 4 bonds. This one has already 2, so we add 2 hydrogen atoms there. This one has already 4, so there are no hydrogen atoms there. And then this one, we put 2 to make 4 hydrogen atoms there. So what is the formula? The formula is now going to be H2, I'm beginning from here, H2, double bond, then C, another double bond, C, H2. Now this compound here is an alkene with 2 double bonds, what we call a diene, but is sharing the same molecular formula with an alkene. And so an alkane is isomeric to a diene. What's the name of this one? This one is 1, 2, 3, so there are 3. But we have on the first carbon atom, there is a double bond. On the second carbon atom, there is also a double bond. So we say this is prop. Instead of saying propane, we say prop 1, 2, diene. Prop 1, 2, diene. So meaning this is where the name is coming from, dienes. Isomeric to the alkane. Another example that we can get of functional group isomerism, we can have C4H6. This is an alkyne. So we have CH3, CH2, C triple bond, CH. 4 carbon atoms. We can create a diene here. If we imagine there is a possibility that I can have a double bond here, and I can have another one here. There's also a possibility that I can have a double bond there, and another one there. Meaning that there are 2 dienes that can come from this. And those are all isomers that are sharing different functional groups, but sharing the same molecular formula as this compound here. So I can write and say there is now an isomer CH. I'm writing now this one, CH3. And then when I go here, there are 3 bonds already, so I need one more. So there is one H there, a double bond, C. There are already 4, so I can't put there. And then there is CH2. We need more 2 there. That is a position, that's a functional group isomer to build one ion. Then this one would be H2. I need 2 here. Then C double bond. There is need of 1 hydrogen here, so CH. Then there is need of 1 hydrogen there still, CH. But then there is a double bond, CH2, like that, CH2. And so that is another functional group isomer. So we can see that alkanes exhibit the 3 types of functional group isomerism. So this is isomerism in alkanes. And next time we shall now look at how we prepare alkanes. Thank you. Tune in the next lesson.